the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 89, where today we're going to be talking about some of the experiments that we have done in our short careers at university.
Yeah.
Short, relative.
Yeah, I mean, we've been doing experiments since first year, which I don't remember
First year
any
experiments
of them, to be
were
honest.
not, yeah. First year physics usually has like a practical part. Assuming most universities have this. Like I know
Yeah.
U of T does, obviously, because we did it. But I'm assuming most other universities where, like, if you're going into a physics line, you're probably in your physics class, you're probably going to have like a practical or like some
Yeah.
sort of experimental part of it. I don't know if you learned too much.
I just
there.
remember one thing. We had a pig with wings tied to a
I
string.
remember that. And it was just going around.
It was
in
going
circles.
around.
Yeah, I remember
You had to
that.
calculate like the tension in the string and the centripetal
force or
acceleration,
acceleration,
yeah.
of the pig. That was fun. So
That was
I mean a big part, and we've spoken about experiments so much on different episodes. Like a big part of like experimental physics is just about taking a scenario that we understand theoretically. Sometimes you don't even have a theoretical idea of something and you just want to experiment. That's a little different, but usually, at least in the scope of our experiments, you have a very good or a very solid understanding of the theory, and you just want to see how it's applied in real life.
I mean,
like
that's
how it
not
works in
very
real
true
life.
though, because from my labs, I didn't really know anything.
No, but the
before going
theory
into it.
exists, is what I'm saying.
yeah,
like
yeah,
what I'm trying
yeah.
to say is that the theory is there.
Okay.
You're simply trying to prove the theory. You're trying to show that the theory exists. But in a lot of experiments, they don't even know if the theory is. They're experimenting before they even have a theoretical model
Yeah.
to see if it works or whatever, right? So there are different types of experiments, but I think mainly, at least what we're going to be focusing on, is the ones we've done, mainly where the theory is known and we're trying to just deduce something about reality, like whatever experiment that we're basically proving,
Yeah.
right?
And there's, a lot of basic experiments that are super straightforward. Like, for example, if you want to calculate the gravitational constant, just G, 9.8, you can just throw objects down and measure how long it takes for the object to hit the ground and do a little bit of analysis on that data. But there are also cooler experiments that you can do, and one of them I did, and I'll be talking about that later.
Are you talking about the hoops?
No,
Did you do the hoop one?
no, I didn't.
Because our very first experiment in my second year of physics lab was where we basically had hoops, like rings of different sizes, and we would like kind of perturb them a little bit, and then we would see their oscillation, and then via pendulum equations we would deduce G. So this is actually a very classic thing. Maybe not the hoop situation, like with different varying lengths, but a very classic situation of like measuring G with a pendulum. I think a lot of people have done this in like high school physics.
Yeah.
Because it's something that kind of introduces you to the notion of experimental physics, but it's very simple. Because you're basically using your equations, root L over G, to solve for because you already know your period in this case, your idea, because you're experimenting with it. You know your period, you know your length, then you can kind of deduce G experimentally. So that's one way to do it, and that's kind of a very famous way to predict the value of G, different heights and everything. This can be shown, is different at differing heights and stuff like that. So it's a really cool intro. But yeah, a lot of people probably did this in high school, but we do get a little more complicated because now we also get into actually inputting a lot of this data into programming software, right? Because it's not only you that's just writing. Like sometimes if you're just taking a couple measurements, if you're doing a couple experiments, you can just take them down and you can just do the average on your piece of paper. But when you're taking like multiple hoops, multiple different experiments, it's a lot easier sometimes to just put it in a program and just have it do everything for you. So there are a lot of advantages to, computerized stuff, which we're also going to get into today because that's heavily oriented in physics. And yeah.
For the hoop thing, could you assume the hoop is just like a regular pendulum?
Yeah, so that was a little weird because I don't think we could, because mass in a pendulum is a point mass, is the idea.
Oh yeah.
But in a hoop, that's not the case anymore.
Moment of inertia
Yeah,
or something
exactly.
like that.
There was a
Yeah.
moment of inertia situation that we also had to factor into it.
Oh yeah.
Because
yeah.
there's mass that's distributed evenly.
Oh yeah, and the parallel axis theorem to bring
Because
it up.
we did have to use that
Yeah.
because what's actually happening in a pendulum is, if you think about a mass, like the way that it's theoretically shown, like the analogy is that it's a point mass,
Yeah.
right? So we have a point mass just moving up and down. The problem with multiple non-point mass is that every like, I don't want to say differential, but like every small
Yeah.
unit of mass is moving. Not only that point. So it's kind of like a generalization. So it was a little harder, like using a hoop versus, obviously it wasn't like a high school physics class. But I'm just saying, like, the idea is still there. Like getting G, like stuff like that is still there. And it's cool how you can do that.
Yeah. All right. So before we start,
I
we
mean,
have
basically kinda-
some news. All right, everybody. Yesterday we hit 19,000 followers on
Yes, sir.
Spotify.
Spotify, yeah, that's just
Yeah.
We've passed 20
Like
overall.
in total, yeah.
Yeah, we have passed 20 overall, but we did hit 19. So thank you to everybody who continues to follow, continues to listen on Spotify. And if you are listening on Spotify, do make sure to go on YouTube and check the video out. Because, I mean, I think if you have been listening, you definitely know that we do videos now. So if you want to come see our faces, go for it. I've seen a lot of comments, and this is interesting from you guys, that you don't think, like, when you hear us versus when you see us, you think we're switched.
Yeah.
I hear so many, like, and I'm like, huh, that's
Yeah.
interesting.
Actually, one person said that they knew exactly which one was.
Really?
Yeah.
Oh,
I
spot
saw
on.
that.
Props to that guy.
So, yeah. What else other than 325,000 downloads.
325,000 downloads. We're
Oh.
really close to the big 500. Really
Very
close
cool.
to the big 500.
Very
so
exciting.
continue downloading our episodes, basically. I mean, that would be dope. On YouTube, we did recently, I know we've mentioned this before, but we're near, no, we're not. We're 2065. I was going to say near 2100, but that's not really true. There's still quite a few. But we're 2065. So we're getting up the ladder, slowly but surely. So again, if you are on YouTube, why not smash that subscribe button? Smash that like button
Boom, boom.
for the algorithm.
And also leave a comment, because every single week we pick a comment as the comment of the week
We do.
and we read it out loud.
We do.
Here on the podcast. This week's comment comes from Yigit3301.
Okay, probably not his name, but okay.
Yeah, they say, love the podcast. It helps with my crippling depression. Well,
I love it.
we are very happy to help.
I love it. I
so
love it.
I'm glad you enjoy the
Well,
podcast.
hopefully you're not cripply depressed, but I think hopefully that was in fact a joke. But hopefully you are okay, and take care of yourself.
Make sure to leave a comment if you want to be next week's comment of the week, and we might just pick yours.
Very simple. Very simple.
Anything else?
I don't think so.
All right. So, do you want to go first?
I mean, talking about, okay, I mean, we can start with a simple stuff. Basic understanding or basic idea of starting an experiment is first getting a little bit into computer science. And before, because I know experiments will take a big part of this episode, I just want to get this a little bit out of the way. Like getting used to coding and getting used to like Python in this case, or like any real language. Python is mainly used because it has a lot of libraries that are very accessible. Matplot, your NumPy, your very big ones that is very accessible to the average individual that they can use to kind of better their code. But the big part of what I'm basically trying to say is that learn code if you're trying to do experimental physics, because what you always start with, and this was a thing that I was luckily okay with because I'd already taken like 3 years of computer science in my high school. But I know a lot of students who, even in first year we were introduced to a little bit of Python, but a lot of students were still struggling there. And then second, it did become a lot harder because it was more rigorous. You had to apply a lot of the things that you understood about it. So it did get a little bit harder. But if you have a fundamental understanding of what's happening in a particular program, I think it makes sense, right? So the fundamental idea is, well, after you input your data, you always want to observe it, right? You always want to just look at different plots. You want to just look at what it's doing, even before you do any analysis, just to see what the heck is actually happening, right? One of the experiments that we started with in my particular class, in my second year of physics, I think that's mainly what we're going to be going over, our second year physics experimental class, was this oscillating mass on a spring, right? And we had two cases, one where the mass was, well, oscillating on a spring, and the other where there was a dampener that was introduced into the system. So it would basically kind of weight the spring almost and dampen the whole system as time goes on.
Well, actually, it was a metal plate that would have air resistance.
Air resistance. Sorry. Again, I have done this course about a year ago, so I don't remember the exact stuff. I will not. I will mention that right now. I don't remember the exact stuff, but I can still give the general idea. And something from this is, well, how do you collect this data? Is, well, you have, I forgot what it's called. What's that thing called?
I don't know.
That like makes those.
It just,
you know what I mean?
It calculates the distance.
Yeah.
From like something to whatever is in front of it, like a motion sensor.
Motion sensor. Motion sensor would basically be it. And what it does is it basically just relays. Does it do light? I'm pretty sure it does light. Right?
No.
What does
no
it
way.
relay?
Sound.
Sound?
I think so.
Probably.
It makes the noise.
Oh yeah, it makes the noise. Yeah, so that's definitely sound, 100%. So it basically simply sends sound waves out. And the idea is when it hits something, the idea is that it will reverse back and follow its trajectory and come back into the sensor. So the time that the sound wave took to pass is known. You know, obviously, the speed and everything of the sound, like the properties of the sound wave, because the motion sensor is the one that makes it in the first place. Mm-hmm. And then from there, you can deduce the distance pretty simply.
Well, you don't have to do anything.
Yeah, no, you don't do it. The motion sensor,
program does
the motion
it for
sensor
you.
does it for you. And where the computational aspect comes in, and you can already obviously tell, you're not recording these points individually, right? Because it's a lot of data. It's a lot of distance measurements.
I think it's like 100 per second. 100 per second.
It was a very, very, very precise data collection process, and something that you would never really be able to do yourself, right? So in this situation, you have this data that you now look at, which basically simply plots the distance over the time, and you notice that, hey, it's sinusoidal. That's pretty cool, because and it's pretty obvious for a spring system what's actually happening, the fact that it's sinusoidal. And with the fact that it's sinusoidal, you can now deduce all kinds of properties from it.
Well, also the program calculates the velocity over time at the same time.
Right? Yeah, the program is pretty cool. The program is pretty cool.
You can plot in Python the position over time, velocity over time, and then you can also do velocity versus position, and you get the phase plot of it. And you see that when there's no damping happening, it just follows this elliptical orbit in phase space, which is expected. And when you do put the damper on it, I guess, something like that, what happens is that the air resistance actually produces a force against the motion of the spring. And so over time, the amplitude actually decreases. And you can actually do it like mathematically and see that the amplitude decays exponentially. And so what you do is you record the data, and to model the amplitude, like how the amplitude decays over time, basically you select the data points that represent like the max height that the spring achieves, and then you actually have to curve fit those points.
We can talk about that in a second.
Yeah. So yeah, I guess we can talk about the curve fit. Well, just very briefly, I guess, because it is kind of complicated.
It's an interesting, complicated thing to talk about.
So the curve fitting function is from SciPy, scipy.optimize.
It's basically another library in Python.
Yeah.
I was unfamiliar with Python.
And so what the curve fitting function does is, well, you input this model function, which is basically what you expect it to follow. Like if you know you're trying to model a exponential function, then your model function will be like e to the x, you know what I mean, or e to the ax.
Yeah. Or technically a e to the bx plus c, because they can be multiple.
You just add you add all of the parameters that you
general,
want.
Exactly. Yeah. In your model function, you want it to be basically as general as possible, because in this case, there are actually functions in other programs. I know there's one in R. They probably use one in Python that automatically models the best fit.
Oh.
Yeah, it automatically models the best function that would work.
Damn.
So there are some really broken pieces of code. But again, that's not the real point. The point isn't to just have it do everything
Yeah.
for you, because you also want to really understand what's happening. So yeah, so basically the model function, you want it to be as general as possible so it can input all the various parameters. And the main purpose of this curve fit function is when you give it these parameters like a, b, and c, for example, as you just said with the exponential decay function, you have a times e to the bx plus c. I mean, they're all your variables in your general exponential. And what the curve fit function spits out, and this is where it gets really cool, all you're really inputting is what your x values are and what your and what your observed values are. So you input your time, which is basically just a linear subspace of 0 to whatever, however long you recorded it for. And then you input your observations.
I don't think subspace is the word.
The subspace, I was going to say linspace for
Yeah.
np.linspace, and then
Yeah.
I just said subspace. I know that that's not the right name, but it's just individual blocks starting basically integers from 0 to whatever.
Yeah.
So, I mean, that's your idea. And your next step is, or after you input your times, you input your observations. And what this function spits out is the best values. Now, I'm going to define best in a second, but the best values for A, B, and C. So
or whatever. You
Yeah.
can have as many parameters as you want.
you can like put in A, you can do A, E to the B plus C X times D,
Yeah.
and it'll still just figure out the B plus C. Like,
Yeah,
I mean,
even
that
if
doesn't
it
make any
doesn't,
sense.
even if it doesn't match your data at all, it'll still give you the best ones. That,
Like you
that
can,
you should use.
I mean, I think we spoke about this in the statistics episode, or like last episode. But like, you can still fit a straight line to curve data.
yeah,
Doesn't make any sense, but you can still do it.
yeah,
Right? And the way that it does it, and I did speak about this a lot, is linear least square fitting. It basically takes the least squares of your residual. Wait, does it? Wait, no. Curve fit works with chi-square, doesn't it? Does
Yeah,
curve
it
fit work
does.
with chi-square, or
It
does it work
does.
with linear?
I think it's chi-square.
I
Actually, I think it's linear. I'm not sure
I'm
because
pretty sure it's just the least square fit, but I
Yeah.
could be mistaken because again, what's basically happening is you're just seeing, okay, out of these, what it does is it models multiple functions and it sees which one of them will give me the residuals, which are your observations in this case, closest, the average, like kind of even on this side, even on this side. And for those listeners, I'm basically saying even below the line and even number of observations above the line. So you don't want something where all your main observations are above your line of best fit or below your line of best fit. And I'm saying line, but I'm saying any function works. Curve, sinusoidal, really anything would work. And the idea is that it simply calculates what are these optimized parameters for whatever values you give it, and it just spits out your model function. It just spits out basically a prediction, right? So based on what you have, it spits out where should this be a little later on. Because the problem with a lot of data is that you only have a limited subset, right? And this is also, I'm always making connections to statistics, but like what you're modeling a sample. Your goal is to predict things about the population, right? So you're modeling 5 seconds of this one spring. Your goal is to be able to model for however long, any mass, any spring. That's your idea. So how do you do that? Well, you obviously can only observe whatever you have with you, but with those observations, you put it into functions like the curve fit function, and it basically can help you predict future values for different values of mass, different values of this.
I mean,
different
actually,
values
you
of
wouldn't
that.
be able to change the spring or the mass because the function that you're fitting.
In this
just-
particular situation, because the spring and the
Yeah.
mass and the spring constant don't actually affect the equation of doesn't it?
Yeah,
M
those-
over K, yeah, M
it's
over
K
K
over M.
does. K over M, exactly. So it would affect the.
Yeah, but I'm saying that when you curve fit your data,
Mm-hmm.
you wouldn't be able to predict anything about any other spring because the curve fit is for that particular spring and mass.
The idea is with your independent variable is what I meant. So like in
Yeah.
this case, time. So I guess yeah, it doesn't really help that much. But the idea is okay if you have your exponential decaying thing for 5 seconds, and you model it,
Yeah.
you'll be able to know what happens.
I know.
after
All I'm
20
saying is
seconds.
that
Sorry,
you
that's
can't
what I
switch the
meant.
spring.
Well, the idea is if in a you're right. In a highly predictor environment, like where you use the spring constant as
Yeah, in
the
that
predictor,
case.
yes, in that case you would be able to do it. point that I'm trying to make is that the main point of functions such as curve fit and things that do similar functions that do similar things is basically just to model predictions, right? It's to model your observation and basically to understand, okay, maybe this will happen theoretically with what I got. And now what I got to do is when I have this model of my observations, I can now compare that to theoretical knowledge that I already have. I'm like, okay, like for example, very simple thing I'll give you here, voltage resistance. You know it's supposed to be linear. So you model it. Is it linear? Does it follow a linear curve? And then compare it to what it should be. And then look at how those lines work. Are they similar? Are they on top of each other?
We actually did do that.
Yeah, we actually did do
Yeah.
a very similar thing. We did the exact
No,
same
the
thing.
exact same thing.
But again, the idea is all there. The idea is just to get observations and to parse it into these functions that can calculate parameters, that can calculate predictions, and then you can analyze the data from there.
Yeah. So let's actually get into a lab, something that is fun. So for our class, basically, the first 3 labs that we did, quote unquote lab, first 2 weeks, you just learn the coding that you'll need, which hopefully you already know, because it would be kind of, I can't really imagine having like learnt for the first time about like lists. That would have been a little bit too much on my plate. But I did know a lot of the things before going into the class. And so the first 2 weeks was just like, okay, you learn everything you need to know about the coding. And then we had 3 Pi labs, which were like the spring mass we did.
Python, no one knows what that means.
Pi labs,
Okay.
Python.
Python
it's
lab.
the word.
Okay, but basically it's just a computational lab.
Yeah.
So it's mainly heavily centered around doing things.
There's
on
just
Python.
like a very simple data and gathering process, and then everything else is done on Python. And we had to write the lab reports for those. One of them was Ohm's law, which we do like circuits and stuff, and the other one was nuclear decay, where we had like this decaying thing, and we recorded the decay count over time, and it decreased exponentially, and we had to do a bunch of Poisson distributions. So that was cool, but it's not the coolest part of the class. The best part is that I think it's like halfway through, or maybe a little bit over halfway through the course, there's like a list of labs that they put out, and you have to choose 3 of them. And I think there's like 15 labs or something. Anyways, they all have like,
There are a lot.
they're all really cool. You get to use like some crazy instruments, and yeah. So you choose 3 of them, but yeah, you really have no idea what you're getting into unless you read every single lab handout, which is a lot of reading. So I didn't do that.
You read all the lab handouts
You read all the lab handouts?
for the experiments.
Yeah. No,
Yeah?
like even the ones you didn't do.
Oh no, of course.
Yeah,
not. Of
that's what
course
I'm
not. Yeah,
saying.
Okay, yeah. Okay.
That's what I'm
I
saying.
thought you're saying in here. I'm like, what?
I'm saying
Okay, no, that
before
makes
you
sense.
do.
Yeah, of course.
Yeah, so I didn't read every single experiment lab handout. So I didn't, like, when I chose my experiments, I was just going off of the name, So I the first one I did was called air gyroscope. And that one so far has been my favorite experiment out of the 3 that I've done. Right now I'm writing my last report. So air gyroscope was the first one. What happens in air gyroscope? All right. So the goal of the lab is to calculate G, which is 9.81. Is to calculate that value experimentally. And so what you're given, this is actually such a cool lab. So you're given a metal sphere, and one of the sides is flattened like a little bit. And so there's like, I'd say, if I remember correctly, the sphere was like 5 centimeters across, and the flattened part was like half a centimeter into the sphere. So it's like a pretty small flat part. And you're also given this plate with a little pocket in it to put the sphere, and then at the bottom and on the side of the pocket there's 2 air holes where you can turn on like the valves, and then air comes out. And so what actually happens? One more detail, the ball is actually magnetized. So if you have the axis, I'll call it the polar axis, and this is the axis that goes across and through the flat spot. And so the ball is magnetized perpendicularly to the polar axis. So it points like on the side. And so what you do is you put the ball inside of the little pocket and you turn on the air. So the air on the bottom of the ball is going to make it like float because it's like high pressure air. And if I remember, the ball was like 1 pound or something like that. Then the air hole on the side would make it spin. And what we had to do was we had to accelerate the ball such that it spun around its polar axis, which is actually kind of a tricky task to do for it to not like spin in every direction. But we had to speed it up to 60 hertz. So we had to make it spin 60 times per second. Now, first question is, how do you know it's going at 60 hertz? And this was actually really cool. What we did is we drew a dot on the ball, and we were also given a strobe light where you can control how fast the light was flashing. And so if you shine the strobe light at the ball and you see the dot on the ball, if the ball is rotating at 60 rounds per second and your light is flashing at 60 hertz, that means that when you see the dot, by the time the light flashes again, if the ball is going at 60 hertz as well, the ball will have enough time to rotate exactly once, and you will see the dot at the exact same place when the light flashes again. And so if you shine the strobe light at the ball and the dot isn't moving ever, that means it's going at exactly 60 hertz. And it's cool because you shine the light as you're accelerating the ball. And so as the ball is accelerating, it gets to 20 hertz. But 20 hertz is 1/3 the speed of 60 hertz. I guess it's not a speed, but whatever.
Value.
So yeah, it's 1/3 the value of 60 hertz. And so what happens is that the light shines, you see the dot at a particular spot. Then when the line shines again, the ball only has the time to spin 1/3 of a full rotation. So then you see the dot at like 1/3 of the way. And then the next time it's at 2/3 of the way. And then the next time it's at 3/3. So then what you see is like this triangle pattern show up on the ball. And then it speeds up even more. And then you see once it gets to 30 hertz, it goes exactly half a rotation for every flash. And then you see 2 dots, and then it accelerates even more. And then it gets to 1 dot, and then it looks like it's not moving at all. Then you know that it's exactly at 60 hertz. What do you do now though? This is the cool part. Remember I said that the ball is magnetized. And so around the actual plate that you have your ball spinning on, there's actually like a wire that's connected to just, an outlet. And the AC current of just, I forget what it's called, like the city power grid or something. Like the current that comes out of the wall is 60 hertz. So the current alternates 60 times per second. Now, if you know anything about electrodynamics and magnetostatics, if you use some of the cool laws that they have over there, you'll see that if you have a ring with alternating current, or just let's forget the alternating part. If you have a ring of current, you use the right hand rule, you put your thumb in the direction of the current, and then your fingers will curl in the direction of the magnetic field. And so the magnetic field, when the current is going around clockwise, is going to be pointing downwards. And then when the current reverses, the magnetic field will be going upwards, exactly where the ball is. And now, remember how I said the ball was magnetized, and the moment of the ball is going around at 60 hertz. And so what happens is that you need to lock the rotation of the ball to the current. So you turn on the current once it goes at 60 hertz. And then the reason why it doesn't slow down is because when the moment of the ball is going from down to up, the magnetic field is pushing the moment upwards. And then when the moment is going from up to down, the current reverses because they're both going at the same frequency. The current reverses and pushes the moment downwards. And so you get this like
gyroscopic kind of.
Well, the gyroscopic thing hasn't shown up yet, but it's just that the ball is not going to slow down because it's constantly being just like pushed along in its rotation. Now, how do we calculate G from this? This is the interesting part. So if you were to place this ball with its polar axis parallel to a table, as you know, the center of mass is a little bit off center, and so the ball would rotate to have the flat spot facing upwards. And so this actually creates a torque because the ball has an angular momentum pointing in the direction of its polar axis. And as we know, R cross F, it's a cross product. That is torque, and torque is the derivative of angular momentum. So torque changes angular momentum. And so the force is trying to change the ball's orientation. But this would be, changing the ball's orientation would be moving the vector for angular momentum upwards. Now, if you use the right-hand rule, because it's a cross product, you'll see that the torque being applied by the force of gravity is actually causing the angular momentum vector to precess around and make the ball rotate. What's this direction? Like around this way, not this way.
Oh,
Yeah.
there's like pitch yaw, and I know what you mean.
Yeah, so
It's
the ball is rotating around its polar axis, but then the torque causes the polar axis to precess around. And you can use the right-hand rule to see which direction it would precess. But how do you calculate G again? Now, notice how the rate of precession is dictated by the force being applied. And so the force being applied is gravity. So at some point you'll be able to isolate for G. And so with the moment of inertia, with the torque, and with the precession rate, you're actually able to isolate for G and solve, using the things that you've measured to actually get G. And so what we would do is we would point a laser at the ball, and we have like a wall right next to us. And so we mark the wall, and every time the ball would make one rotation, the laser would reflect off of the flat spot and onto the wall. And every time the dot on the wall would cross a line, we'd take a measurement. And this is insane to me because the rate of precession was around 10 minutes. And so we would take a measurement, and then we'd wait 10 minutes, and then we'd take another measurement. But every single measurement that we took was within half a second of every other measurement. So we would take a measurement, 10 minutes would
you
go
take the
by.
measurement manually?
Yeah, we'd just time it.
Yeah.
So we'd take the measurement, the ball would go around. 10 minutes later, we'd see the dot come back on the wall, and we'd get ready to time it. Once it hit the line, we'd time it, and it was literally within half a second. Now, 10 minutes is 600 seconds. And the the precession was so constant that it came down to that level of precision. So that was crazy. So then, we took our data, we took our precession rates. We also measured the diameter of the ball, the length by which it was flattened by. We measured the mass, which you actually didn't need for the calculations, but we measured it anyways. I think that's all we had to measure. And yeah, with those values, you can calculate, you just plug them into the equation. You also have to do some more analysis, like error analysis. And it's not so straightforward. It's not just plug in the values and you get the answer. You have to do a little bit of analysis. But yeah, we ended up getting a pretty good value. I think we got like 9.79, which is pretty good. And it was a very cool lab. It was very cool to just look at the ball spinning. We'd like change the frequency on the strobe light, and it would be moving in like all types of crazy ways. Yeah, that was very cool.
Strobe lights are cool. I know I had one for my experiments too.
Yeah.
And I think one takeaway from a lot of these experiments is that you're not always going to get the actual answer.
Yeah.
Like having an answer that is not even right though is not even bad. Because as long as you explain why that happened under the right context, it can still make sense. Because sometimes, there can be an effect, sometimes there can be a predictor, sometimes there can be something in your experiment that's messing with it that you did not know before. So you write down your measurements this way. Because a classic thing that a lot of people do is they try to fit their data with what's theoretically known. But the thing is, even though that is what you want to get, that is not what you want to do. Because that's always your first step into basically a bad data analyst. Because you never want to remove data just because it doesn't fit the model. That's terrible. That doesn't make any sense. You can't do that. Like, there's a reason for why it's skewing the model. And unless there's a contextual reason for why you can remove it, you can't remove it. So in this situation, you got 9.79. I'm assuming no one really got exactly. I mean, no one will ever get like exactly. But the idea is, well, you can get more and more precise, but you're never really going to get that exact number, right? Yeah. And that is, in essence, like one of the characteristics of experimental physics, right? Like if you go into it thinking that, okay, I know what I have to fit, it has to look like this. Why isn't it looking like this? You're not going to do well. You're just not going to do well. Because you have to take in whatever data that you've been given or you've acquired, and you just have to analyze that in the most respectful way possible, without really removing, without really touching. And that's why that's really important. Not getting the exact answer is not always bad. Another experiment, an experiment that I did, I wanted to talk about the black body thing, really cool. But I wanted to also talk about something small, which is a wave phenomenon. There was this title of the experiment. And this was actually a pretty cool one because it wasn't actually something that we were determining. There wasn't like a goal because usually when you're trying to do an experiment, you're like, okay, I want to find this. I want to solve for this. I want to calculate this. This experiment, there's nothing really like that. It was just observe the effects of waves. And I thought that was pretty cool. So basically what we did, very simple setup. We set up this ripple tank, basically this tank that like had a mirror at the bottom so that the light would reflect and show to the observer on a screen. So basically what would happen is on the top, you could put water, right? And you could put all sorts of objects on the top, right? So for example, what we started with was like a straight barrier. And then we did like a curved barrier for reflection and stuff like that.
And you'd send waves
water
to
waves.
the barrier and see how
water waves to the barrier basically. And what would happen is there was a strobe light on top, and there was a camera that was situated on the screen, on the other side of the screen. And what was basically happening, super simply, it was just the light was going through the water, reflecting on the mirror that was at the bottom. It was set up at an angle such that it would reflect onto a screen. And that screen had a camera on the other side of it that then would basically record whatever you see that's happening here. So that was, a very, very simple experiment there, like very simple setup. But what we did was really cool. So like we started off with like some really simple reflection, just like putting a straight barrier there. So it was a transparent barrier. So you could actually see, water if it, it obviously didn't go because it was opaque, it was solid. But I'm saying it was transparent it was also a black and white image. So I don't know if that really changed much. But what the purpose of this was basically to send water waves with two dippers or with a dipper. What it would do is basically this small dipper, as it is called, would basically oscillate back and forth. And if you put it close enough to the water, it basically creates ripples. And this ripple, the wave, the frequency of the ripple. So from there, you can kind of deduce properties about the wave itself.
Did you have a barrier with two slits in it and you can see? Oh, that's cool.
Yeah, we did.
That's really
I was
cool.
going to talk about that. So we started with the simple reflection stuff. We did a curved barrier. We did concave and convex. And we basically modeled, and we tried to model, like with the picture, how the water wave would basically reflect from the barrier, right? And then for refraction, which was really cool, what do we do for refraction? How did the water go through it? I think for refraction,
it's like one slit.
Because remember, what's actually happening is
that
the light is being reflected, and we can see what's happening there. Because again, okay, as I did mention before, I did this like a good year and a half ago. So like, bear with me here. I am forgetting some of the exact details. But the idea was that the light would kind of come onto the screen and it would showcase an angle that it went. That doesn't make sense though. How would the water? I think it was the light. I don't think it was the water in that case, because in the refraction experiment, obviously the water wouldn't be able to, like, that doesn't really make any sense. It would be the light that's actually refracting through the transparent barrier. So we kind of were modeling that too. But anyways, all of this to come to the coolest part, the interference part, the interference and diffraction. So we started off with a single slit, which was just for diffraction and to see how water diffracts from the slit, like the angle of diffraction. And using principles of diffraction, we basically were observing how the water moved after it passed by the slit. So before and after the slit, what the difference in the motion of the waves were. And we kind of finished it off finally with then interference, then we had two slits, like the double slit, the classic double slit experiment. And we basically did this with water waves. And obviously, because interference happens in any type of wave, the fundamental, like we actually use like psi and stuff like that to calculate, even though it's nothing really to do with quantum mechanics, we still use like the properties of a wave function to estimate interference patterns. So that was actually really cool. And we actually saw, like, I mean, I don't know if this is, this kind of is like the double slit experiment. It kind of is.
I mean, it is.
I mean, it totally is.
Yeah.
I know, it totally is. But I'm just saying it's not exactly like the same setup, obviously. But the fact that I saw a double, like, I think that's really cool. I think that we actually, performed the double slit experiment with water waves. I think that's something that's really cool. Because again, the whole point of this is that the water wave fundamentally is not that different from an electromagnetic wave, and is not that different from a wave of any nature, really. That's the whole kind of the moral of the lab here, that you can apply these principles of water waves to any wave, because the whole generalization occurred when, again, as I was saying, we were using psi, which is usually the term used for the wave function, which is a lot of, in quantum mechanics, a lot to do with basically properties of systems and stuff like that. And in this case, we were kind of generalizing it, obviously, to water waves. I think usually you don't really see that. And I think kind of seeing a real life double slit experiment was definitely really cool. Again, no real goal of this lab, so like not really much to say, but it was just different things that we were observing and different phenomenon that we were observing that are definitely really cool. I just wanted to bring them up because I know some people might be like, oh, that's interference. I can do that at home. Like, you can do this at home.
You could.
Probably
Except
not.
You don't have like
actually.
the sophisticated
Actually,
cameras.
Probably not, because no, it's not only the cameras, it's also like the dippers. You need to have a good, like, you can't just like one ripple. Like, that's not really gonna do much. It needs to be continuously rippling the water, right? So from that, basically, you can get the equation of the water wave, right? And once you have the equation of the water wave, you are now modeling what happens to this water wave when you are sending it through different slits. We obviously were changing the size of the slits, to like observe different patterns and stuff like that. Like, how does the slit size change what we see and stuff like that? And again, you don't even think about doing this on a realistic level. Like, you only think about this as, oh, Young's double slit. You only think about this as, oh, professionals do these experiments in labs. But no, you can literally get like a tank of water and you can do this like in any university lab. And I think that's really cool. Applying these really complicated concepts to a very simple model, and then using that model to once again apply it to very complicated concepts. And that's in essence like one of the main ideas of experimentation. Okay.
Should I talk about my thermal motion or ultrasonic sound waves in water?
Both are really cool.
Yeah.
I personally haven't heard thermal motion because I haven't done it.
Okay, yeah. So I'll say thermal motion.
You can do thermal, I'll do black body, and then we can go into velocity.
Yeah, sure.
Okay.
So, my second lab was called thermal motion. And so there's a lot of theory in the lab handout that you had to read through before going into the experiment. And if I had to summarize it, basically, we're looking at the random motion of small beads
What was your
in
goal
water.
of the lab?
to calculate Boltzmann's constant.
Oh, okay.
So
Okay.
basically, we're studying Brownian motion.
Oh, no way. Really?
Yeah, I told you this.
Wait, I don't remember. Wait, you were
I told
this was
you
in the
this.
lab? I
Yeah.
didn't know this. I actually, well, maybe I just forgot.
So,
That's cool. That's really cool.
so we have water with very small beads inside of the water, and I think, if I remember correctly,
Yo, you just did this.
I know, but it's a weird number to remember. The diameter
Oh,
of
the
the beads was like 0.5 micrometers, or it was like
So
or
tiny.
it was like
Very,
5
very tiny.
micrometers. Yeah,
Okay.
very small beads, and
So you can't differentiate them.
not with your eyes.
Yeah, exactly.
So what we would
Yeah.
do, and these beads actually glow in UV light. So we have these like really expensive microscopes with these UV light sources that shine through the microscope, and also cameras hooked up to it, hooked up to a computer. And what we did is we put this solution with the beads on it, or in it, on these microscope slides, and you'd put it under the microscope. You'd turn on the UV light source, and you'd go in, you'd focus on the focal plane of the beads, and you'd find them. They're very small, even in the microscope. But good thing is that they glow, right, in the UV light, so you can spot them through the binoculars, they're called, where you can see with your own eyes into the microscope. So what you do is you spot some beads, and then you switch the microscope to camera mode, and then you would see the frame on your screen. And this was pretty cool. We had before the motion tracking, we had like an image capturing program where you can set like the amount of frames and the amount of frames per second, and then you just click go, and then it would just record frames out of the camera. And then it would just record frames out of the camera. I forget how many beads we did this for. I think in total we got like 22 data sets for like, you can get more than one bead in the frame. So what you would do after you capture all these images, it would save in, like, we did 120 frames, 2 frames per second, and all of these would just save into a folder. Now, there was another program. This was a motion tracking program where you load your folder of frames. You clicked on the first frame, and you'd click on the object that you want to track. And I'm pretty sure this program was designed specifically for this experiment. So
A lot of them were.
yeah,
A
so
lot of them were.
it's not like it can track like elephants. You know what I mean? Like
Yeah.
it was made to track beads. So you click on the bead, and it would actually use like the centroiding technique that we were doing in AST. Oh, we should talk about that. Let's talk about that after this.
Yeah.
Okay,
that's really cool.
So basically it would take like this center of mass approach, except replace mass with brightness to approximate the center of the bead. And then it would just go through all the frames, and it would tell you the pixel position of the bead on your screen. Now, you might already be able to tell that the amount of data that we had to go through was intense. So we had the X and Y pixel coordinates of, I don't know how many beads we had 22 data sets. Each data set had like 2 to 3 beads in it. We only selected the really good ones that we went through as the motion tracker was going. We're like, oh, this looks like random motion. So we'll pick that data set. We ended up, I ended up importing 18 different beads, like the data sets for 18 different beads. And each data set had the X and Y pixel coordinates for 120 frames. And so you import all of that into Python, and then the analysis comes in. So first of all, this was all in like the lab handout, all of the theory. You know that for random motion, the average displacement in the X and the Y is equal to 0. But the average square displacement actually increases linearly in time. Also, in statistics, if you have 2 variables that are unrelated or uncorrelated, is that the word? uncorrelated. Like if you have two uncorrelated variables, if you take the norm of those two, so you square them and then square root them, or square them, add them, square root it, then that should follow a Rayleigh distribution.
Oh, you mean like quadrature?
Yeah.
Square them. Okay, yeah.
Yeah, so that should follow a Rayleigh distribution, which is right skewed. It's close to, it like starts at zero, it goes up and then kind of like goes down as like 1 over x. It's not exactly, you know.
Is it Riley or Raleigh? How is it?
It's Riley. It's pronounced Riley.
Oh, Riley? Okay.
Yeah. So we knew that much. And they gave us the equation for the distribution and all that. And so what did we do? Well, there were a lot of for loops happening because we had a lot of data sets and a lot of data in every data set. So firstly, we have pixel positions. They gave us the conversion from pixel to meters. Each pixel was like 0.1 micrometers. So you just multiply all of those by the conversion. And because you don't care about the absolute coordinates, you just care about the difference, because you're looking at step sizes between one frame. Like where does the bead go from one frame to the next, because it's random motion. And so a step size would just be, well, the coordinates of the final position minus the coordinates of the first position. And then you use Pythagoras theorem to find the step size. And so you do that for 120 steps, or technically 119 because it's I minus 1. So 119 steps per data set. You do that for all of your beads. And then you just plot a histogram. And I actually had a lot of trouble with this at first, but it was just a small mistake in my code. As soon as I fixed the mistake, we saw that most data sets were very nicely Rayleigh distributed. Everything looked very well. Now, the next step was to curve fit this distribution, because it turns out when you take the knowledge that you know about Brownian motion, right? Random motion of very small particles depends on a lot of variables. For example, how big are the beads? What's the temperature of the water? And other things. I'm not going to name them all right now. The viscosity of the water, another example. So one thing is that we had this diffusion constant. And the diffusion constant, you can kind of imagine it's... I always, when I think of diffusion constant, I always think about T when you put it into the water. And it's kind of like, if you have a high diffusion constant, that means when you look at the T diffuse into the water, if there's a high diffusion constant, then the T will go into the water very quickly. But let's say the liquid is very viscous, or the T is weird and the diffusion constant is low, then the T will take a very long time to diffuse. Makes sense. And so actually this kind of makes sense if you imagine the Rayleigh distribution. If you don't know what it looks like, just think of like a normal distribution,
but right skewed.
So for high diffusion constants, for low diffusion constants, am I getting this wrong? For high diffusion constants, the step size would be larger. Yeah, that's right. For high diffusion constants, the step size would be larger because, think about the tea bag, right? The particles diffuse faster. And so in between one frame to the next, the step size would be larger.
Yeah, that makes sense.
And then the smaller diffusion constants would have very small step sizes on average. And so you can kind of tell how the Rayleigh distribution spreads out. For low diffusion constants is very close to zero, and it's a very skinny low variance. And then as you increase the diffusion constant, it just like smears out to the right.
So you are knowledgeable of your diffusion constant. Like that's your control variable.
That's what we're curve fitting.
That's what you're curve fitting. Yeah. Okay, sorry. So
because
that's your response.
Because the diffusion constant is related to the Boltzmann's constant.
Because I'm like, there has to be some connection between your Boltzmann.
Exactly.
And, yeah, has to.
So what we did is we normalized the histograms, and we curve fit the histograms with the Rayleigh probability distribution function, which depends on the time of your time step in between two frames, but that was a constant because you use the same time step. And it also depends on the diffusion constant, but that was the thing we're trying to optimize for. So we use the curve fit function with D as our parameter. And then we just spat out all of the diffusion constants for each data set. After that, there's something called Stokes drag, which depends on the actual property of the bead itself.
And
like
this is something like general in what is Stokes drag?
Stokes drag, it's like it's
Roughly.
it's a quantity in fluid dynamics, I guess you can.
I guess yeah,
like
yeah,
like
it would be
fluid.
fluids.
Yeah, so imagine you know the wind tunnels where they send smoke
Yeah.
into objects.
Yeah.
Like if you have a high Stokes drag,
Okay.
basically there's like a high drag, you know, like like if you have a flat plane, there's gonna be a lot of drag.
Yeah, that makes sense.
Versus if you have like
If you
an
have like
airplane,
Like an
then there's gonna be a very low drag. Aerodynamic.
Aerodynamic. Yeah.
So the Stokes drag has to do with like how much wind resistance are you feeling? Well, not like
So what's
resistance.
Stokes drag versus just drag? Like, is there?
Well, it's
what's
just
Stoke?
a quantity to like
Oh, it's like a formal measurement
Yeah,
kind of thing.
exactly.
Okay. So it's like a type of drag.
yeah.
Okay.
And just so everybody knows what I said, it's just my understanding of it. I have not done anything outside of this lab with Stokes drag, but
it has nothing to do with Stokes.
no,
Okay.
no.
Just had to
No,
mention it.
it's just his variable.
Same name.
It's just his quantity.
Okay.
But yeah, that's my understanding of Stokes drag. So we could calculate Stokes drag. It depended on the radius of the bead and other things. And to calculate Boltzmann's constant, what you do is you actually relate. So this goes back to the theory in the beginning, where they talk about how the square average displacement increases linearly in time, and it's actually proportional to the diffusion constant. And so Einstein also had this whole thing where he found that the diffusion constant was equal to something, and that relates to the first equation. And so from there, you can isolate for the diffusion constant, and that had, if I remember, it's Stokes drag times Boltzmann's constant divided by temperature.
Anyways, Boltzmann is in there, which is what's important.
Yeah.
Boltzmann is in there.
So we have temperature, we have Stokes drag, and we
Beautiful.
have diffusion constants
Beautiful.
that we optimized for.
Beautiful.
So then you just solve for Boltzmann's constant. Doing uncertainty for this lab was really hard. And
did you get a value that was in like was it in the range of Boltzmann's constant?
no.
How off was it? Like really off? Or?
Well, our analysis was pretty complicated. Like some of our values gave values that are very close to Boltzmann's constant. Boltzmann's constant is like 1.38 10 to the minus 23. And we got 1.5 10 to the minus 3. But this was only for like 3 out of our 18 beads. A lot of our beads gave us like 5 times or 8 times Boltzmann's constant. And actually something that's a little bit unfortunate is that I looked back recently at my code and I saw something that I did wrong.
Oh no.
Yeah. And if I would have fixed it, it would have been way better. But I gave like an explanation as to why some of the beads gave us some good values and to as
See,
why.
as long
like,
as you analyze why your
I
outliers.
tried
are
to
there.
come up with an
Exactly.
explanation, but now that I realized that it was actually something in my code, I'm like, wait, maybe maybe that explanation was not the right answer. I should have just been like bad code. But
That's tough.
anyways, it was a fun lab. It was cool. And yeah, we got to calculate some fundamental constants.
That's really dope. I want to talk about my last lab though. Black body radiation.
We're not going to get to AST
Yeah,
labs.
I know.
That'll have to be another episode because those are really cool.
Yeah, so we also are in, I think we mentioned this before, but Parker and I are in an astronomy lab course. Is this the last one? Is there any 4th year lab course? Oh, there is. Oh, 3, like the theoretical is the last year for this year. Yeah, you're right. So we're in the 3rd year of astrophysics labs, and we have some really cool labs that actually we were also thinking about integrating into this episode, but it is looking less likely, so why not? We can make a new one out of that. But I did want to talk about my last experiment, which was black body radiation. This was really cool because this is straight up exactly what you would do if you have a theoretical relationship and you want to prove it.
Well, actually, our last lab was a lab that we both did, which was ultrasonic.
Velocity of ultrasound. Was that also? That was Debbie Sears effect. That was.
Yeah.
Was that? That was nothing, but that was just like like that was just calculating things about the.
No, I
water.
know, but you said this was your last lab, but we only talked about 2 each.
Oh no! Sorry.
Yeah.
I meant like this is the last lab that I did in my class.
okay.
Sorry.
Yeah.
This is like my experiment because we have 3 experiments. So my 3rd experiment was this one. Is what I meant. And yeah, so basically, there are 2 very famous laws in black body physics, I guess.
Just physics.
Okay, yes, physics. Anyway, Wien's displacement law and the Stefan-Boltzmann law. Those are very, very, very crucial.
Wait, hold on. If I remember correctly,
Yeah, why not?
Stefan Boltzmann is like sigma T4. Is that it?
Yep.
Yeah.
Intensity equals sigma T4. And so okay, I kind of got ahead. But so Wien's displacement law relates the maximum or the peak wavelength of any body's emitted radiation with its temperature. And it states that when you multiply, or the relationship between this maximum wavelength that this body emits and the temperature is constant. That's basically the whole thing. Oh shoot, that's crazy.
Which is actually insane.
Which is pretty cool.
Yeah.
Which is pretty
Yeah.
cool by itself. Which is like, wow, that's pretty interesting to think about, you know?
And you know what's even crazier? I'm pretty sure, if I remember, in last year, in our astro, we had a computational assignment, and we found that the peak wavelength emission of the sun is green.
Wait, did we?
I'm pretty sure we did. But it's just because it's like a mix of a lot of colors that it doesn't look green.
Also probably because of Rayleigh scattering in our sky and stuff, because
Yeah.
it's scattered and diffused all over.
Yeah.
I guess, okay, that's cool.
Yeah.
That's pretty cool.
Yeah.
So fundamental idea about black bodies, again, spoken about this a lot of times, but if you're a little new to the topic, every body in essence is a type of a black body. There's no perfect black body that exists in the world. What is a black body? Basically a body that absorbs and emits radiation. Very simple. And there's no perfect black body in the sense that perfect black body is it radiates all of the absorbed radiation, right? That's the perfect black body. But
Yeah.
there's nothing really like that. Or like, anyway, point being made is that all bodies emit radiation.
But actually,
Right.
stars are the closest approximations.
Yes, you're right. Stars are the closest approximation.
Actually, cosmic microwave background radiation is the
Yeah,
closest.
no, you're probably right, because
is the
that's very
closest.
accurate.
Yeah.
That would probably be
Yeah,
very...
it is. But stars are good.
Stars are
Stars are
definitely
good.
good approximation for black bodies because, again, they emit a lot of the spectrum of light, a very, very large range of spectrum, which is exactly the purpose of all black bodies, that it basically emits your whole spectrum. And the goal or the idea is that as you heat a body up, it starts to glow. Or in the visible spectrum, it starts to glow. But in reality, what's happening is as you're heating the body up, the wavelength, the peak wavelength of its emitted radiation is decreasing as the body gets hotter and hotter and hotter and hotter.
Wait, the peak wavelength? Or
Yeah.
frequency?
Peak wavelength.
Okay, I was thinking frequency.
Peak wavelength
Yeah.
is decreasing,
Yeah.
right? As your body is getting hotter. And what's reason for this is because remember, wavelength decrease means frequency increase means energy increase.
Yep.
So that means as you're increasing your temperature, you're increasing your energy, which totally makes sense.
Did I do the waving arm analogy? Where like, imagine you're waving your arm up and down at a certain frequency. If you increase the frequency, it takes more energy. So that's why it's higher energy when you're waving your arm.
I guess, yeah. I guess that's not a bad way to think about it. Yeah,
Yeah.
I guess that's not a bad way to think about it. Yeah.
So
it's
if you have a short
Yeah.
wavelength, you have to wave it really fast, and that takes a lot of energy. So it's higher
So
energy.
that's a fundamental idea of all black bodies, right? That they emit this thing. And then the Stefan-Boltzmann law comes in where it basically relates your intensity, which is your power over area, and to the temperature by this one constant. But anyways, the point is that it relates the power or the intensity of the light with the temperature. So these are your main equations. And our goal in this lab was basically to prove that these equations actually hold, right? With actual experimentation. So this was actually really cool. So we had a spectrophotometer, which is basically a spectrograph, but a little different because it plots it against wavelength. So it takes the spectrum that's emitted, and it plots its intensity versus wavelength. And what it does is, or what you do is, in this particular experiment, we had a sodium lamp that was set up, and we were basically changing its voltage. Now, remember, or I don't know if we spoken about this before, but voltage is also related to temperature in a directly proportional way. That means as voltage increases, so does temperature. And you can kind of intuitively think about, like, you can kind of intuitively understand that.
This has to do with resistance, though.
No, but you're keeping resistance constant because it's just the same lamp, right?
I know, but like if you want the intuitive picture, it's
Oh,
kind
yes.
of like
Yes.
because
Yeah, maybe go
voltage
for
is like a difference in potential, so you can think of it as like the gradient. And so let's say you have electrons on a piece of wood, and then when you increase the voltage, you're just inclining the piece of wood and you're making the electrons flow.
Mm-hmm.
But you can think of as you increase the voltage, what happens is that the resistance is like friction, and so
Mm-hmm.
as the electrons go faster, there's more friction, quote unquote, and then there's more thermal energy being transmitted.
So yeah, there are a lot of parameters that we do have to control in this particular experiment.
That was
but-
not physical, by the way. That was just a way to think
way to
about it.
understand it. just a way to intuitively understand it. But a lot of parameters in this particular experiment, and we just had to basically vary the voltage. And what we were doing is we had the spectrograph or the spectrophotometer that basically would pass by this, or we would have to move it manually as it passes by the whole spectrum. And what it does, you have to do this very slowly because, again, otherwise the reading will be inaccurate. What it does is it basically, as the light is coming in, whatever wavelength that it is measuring, it measures the power per unit area.
But are you saying like there's a gradient in the intensity of the light, and you have to go through?
No, so
Like
we
some
just
parts
had
were
to,
hotter?
No, because the spectrum took up a spatial coordinate, right? So we had to physically move it across the spectrum to get all parts of it, is what I'm saying. Because what actually happened is what the light would be split by a prism, which would kind of
Okay, that makes
principle of
more
spect-
sense.
of
I was like,
spectrograph.
how is
Yeah.
this even?
So it's split by a prism, and then that basically light gets reflected, and then you
Okay.
move across that range
Yeah.
to get all of your wavelength values. And what the spectrograph is basically, or spectrophotometer is basically doing, is just taking, or whatever light that's being emitted, it is able to measure the wavelength and then calculate the power
That's really cool.
of the light. And
Wait,
therefore
was
the
it
intensity.
visible?
Yeah.
So could you
I
see?
have some really cool pictures.
I'd like to see those.
Yeah.
Could you see, like when you send it through the prism, could you see where, like which ones were brighter than the other? Like you can kind of visually see like the
You
intensity.
could actually see different colors getting brighter. Yes, you
That's
could
cool.
see different
That's
colors
really
getting
cool.
brighter. You could also, number one, obviously see the lamp itself getting brighter as you turned up the voltage,
Yeah.
which was your number one thing about, okay, temperature, voltage, and intensity are all related.
Nah, the prism thing is way
But
cooler.
the prism thing is also
Because
pretty
it's like
cool.
it's like like level curves of the black body thing. You know what I
Yeah,
mean?
basically.
Like you see it's dim and then it goes up and then down.
Because you get that
and the
for different
intensity.
readings, and then you can monitor where the wavelength was the brightest, or the peak, basically. And now, using all of these peak wavelength information, basically, again, we have all of these different sets of data with different different voltages and different wavelengths. We already have a relationship between voltage and temperature. So now we have a relationship between wavelength and temperature. Bada bing, bada boom. And you basically kind of, plot it. And what you do is you curve it once again. So once you have your wavelength and once you have your temperature, if you simply plot them against one another, you know that the relationship should be should be 1 over t. Or is it t, or is it t to the something?
Where are you plotting wavelength?
It's t to the something, probably.
What are you plotting?
A wavelength versus temperature, because the equation for Wien's displacement law is max
Yeah.
wavelength times temperature.
So it's more.
Is it to the power of anything?
No, it's divided. It's the constant
Yeah,
divided by
this
temperature.
equals a constant, is what I'm saying. But is it just temperature, or is it
Yeah,
temperature to the 4 or
temperature.
something? It's just temperature. Okay. So your idea is that when you have your lambda and you have your temperature, your slope, so number one, it should look linear. If it doesn't, probably done something wrong there, because that should not happen. And number two, what you should be seeing is the slope value that is equal to your constant that is predicted by Wien's displacement law.
Wait, why is the slope linear? Shouldn't it be 1 over x? Like, shouldn't the function be 1 over
One second,
x?
now I'm thinking. Because what we did... No, I think I'm messing up the Stefan's law part. Again, bear with me here because I have forgotten. Yeah, the Stefan's law part was linear. Yes. Sorry. Yes, I remember this. Yes. Sorry. What I'm talking about right now is the intensity versus temperature to the 4. That's why I was asking for the power, because I was getting confused. Intensity versus temperature to the 4. Yes.
That's linear.
Yes, that is linear, because what that slope equals is your Stefan's constant, your Stefan-Boltzmann constant, which is another thing that we were actually showing in this experiment. And yes, that was the slope. Sorry, the other thing was not the slope. Scrap that. So that was basically simply via comparing multiple peak wavelengths and multiple temperatures.
Damn.
We were able to estimate that this is the constant, and it was very close. Or not we, it was just me this time.
Yeah.
It was just me. But anyway.
I actually would have rather done this experiment over thermal motion. That sounds like
This was my I had the most fun in this experiment by far. Literally every time I would ask the TA, like, hey, how do I do this? And he would show me something. I'll be like, that's so cool. I would like literally like, be jittering. I would be, because some of the stuff was really cool. Like how you're moving it across to like view the spectrum of this light.
Cool.
Like how dope
Which
is
room
that?
was that in?
This was in second. I don't remember. It was the same. It was the same velocity room. It was just to the side.
That one.
It was to the side. It's such a big room. It's to the side though, because the velocity you enter the room and it's on the right.
Not different
Oh,
room.
okay, different one then. Okay, never mind. Because
Like,
I had it on a different year.
You
too.
know, like the lab room with all the computers, like the main room.
Oh no, we don't do it there.
We weren't
don't
in
do
there.
it.
We were across the hall, and then there's like a room, and then there's another door, and you go into that room.
Yeah,
where
that's
we
the
do
room
it.
that I was in.
Oh really?
Yeah.
Okay.
Yeah, and they completely the
Okay.
photoelectric effect was there. Do you remember the experiments that were in the room? The photoelectric was there.
No, it wasn't.
Velocity was there.
No, it was polarization of light.
Polarization, sorry,
Yeah.
not photoelectric. Polarization
Yeah.
was there. Yeah, so it's the same room. Anyways,
Yeah.
probably just misinterpreting like where exactly it is. But yeah, same room is what we're talking about. And yeah, this was just done in the corner, and super, super cool, because basically you get to show that Wien's displacement law holds, which is really cool by itself. The fact that the peak wavelength of any body, because remember, we're changing various voltage values, so we're testing for different values too. So we are taking into different considerations. So we're saying for any body, these things are constant.
That's very cool.
And then we show that not only is intensity or your power over area related to temperature, but and we solved using the Kerfit function for the Stefan-Boltzmann constant, which is really cool.
Yeah.
Which is really cool. Which is some stuff that we did. So all in all, yeah, I love that class, man. I absolutely love that class.
Yeah. I think we'll do another episode where we talk about ultrasonic waves in water, and also our astronomy labs.
Yeah, our astronomy labs are really cool for anybody who's like interested in like, well, astronomy really. For anybody who's really interested in astronomy, a big part of that is telescopes. Telescopes, data, because when you think of astronomy, you're like, oh, theoretical black hole space. Like, I know how to do calculations, but that's just like a tenth of it. That's not even half of what astronomy, or at least the real analysis part. Again, we're mainly focusing on experiments in this episode, but like that's not even really what it is, because the real essence is when you get these gigabytes and gigabytes of data, and then you have to analyze them through like 1 and 2 functions, try to make it as most efficient as possible. Because another advantage of something like astronomy is that it makes you code efficiently. Because when you have like 2-3 data sets with like 30 observations, you're like, oh, 30 times I have to measure something? That sounds like a lot. But in the astrometric data, you're talking about like thousands of observations and over multiple different time periods, right? So it's a lot more data that you have to collect, and all of it just kind of stems from just understanding a good idea of computational physics and then applying a lot of the ideas learned there into these higher things. So we can definitely talk about our astro labs, because they were really, really cool as well.
The next semester ones are going to be even crazier.
To be honest, you want to wait for that episode then? Because I think the
Oh,
next,
yeah.
because that would be so
Yeah,
cool.
that would. I don't know. Actually, we have
We can do
have
two.
time to do
yeah,
both.
we can do both. We can just
Because
do both.
talking about those ones
Will
are going
probably
to
be
take up a
episode.
whole
Will probably
episode.
be a whole
yeah.
episode. Because the next semester,
Maybe even more. Because it takes so long to explain,
Yeah,
like
you're
the
right.
lab that we're doing now.
You're right.
That would take so long.
I mean, a little glimpse into our next semester. So one of our experiments, or our last experiment, and this is the craziest one, is literally titled "Modeling the Milky Way."
mapping.
Mapping the Milky Way.
That sounds like the craziest lab.
Like what? Like
That's gonna be so
incredible.
cool. That's gonna be so cool.
Mapping the Milky Way. Like I don't even know what we do. It sounds so cool.
That's gonna be really
Like
cool.
that's definitely a whole episode. We have some really cool labs next semester that we can talk about. But even the
Yeah.
ones we did this semester were really cool because it's still just an intro into understanding like how we have data from a telescope. What do we do with it?
Yeah.
Right?
Next
'Cause-
semester we also have labs on exoplanets and labs on pulsars. So
that's gonna be so cool.
that's gonna be cool.
Yes, sir.
Anyways, this is the end of the podcast.
It is the end.
Matt, we just cut it there. Thank you so much for listening to this episode. If you enjoyed it, make sure to follow us on Spotify. Get us to 20,000 followers.
No, sir.
Also go to YouTube. Even if you don't watch us on YouTube, just hit the subscribe button and then you can leave, And then also leave a comment of the week, and also do some other stuff. Thank you so much for listening to this episode. This has been episode number 89 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we shall see you soon.
Bye, guys.